Hello and welcome to this lecture. My name is Miracle Chibuzor Marcel and I'm from the Pan-African Citizen Science Laboratory. So today we are going to be learning about variable stars. So the topic of my lecture today is an introduction to variable stars. So you can see those stars there. So they are variable stars. And we're going to learn why they behave that way. So as part of the table of content, I'll be treating variable stars. I'll be explaining what variable stars are. Then I'll talk about the groupings of variable stars. They are grouped into two. We have intrinsic, we have extrinsic. Then I'll be talking about, so I'm going to be focusing on the intrinsic part. Then I'll be explaining different classes of intrinsic variables like pulsating stars. Then we have eruptive or cataclysmic stars. I'll also be giving examples of pulsating stars, explaining a little bit of them. Then I'll also come over to eruptive, cataclysmic, explaining what it means and some of examples. Then I'll come over to extrinsic. So these are the things I'm going to be covering today. But I may not be able to cover all the things about variable stars, but for today I'm going to be covering just this few. The next time I'll cover the rest. So by the way, this lecture is sponsored by Free Astro Science Group. So what are variable stars? A variable star is any star whose brightness, okay, we call that apparent magnitude in astronomy, okay, whose brightness or apparent magnitude as seen from Earth changes over time. So that is called a variable star. So if you look at this picture here, you can see that this star is changing in brightness. Okay, see the dates, the images you are taking. You see that over time, over the years, it has changed in brightness. Okay, so and if you look at this star too, you see that it is changing in brightness. Okay, so a lot of stars are like that. A lot of stars are like that, and we call them variable stars. Now, this occurrence is not something that we are used to, and it is not something you can see with your naked eye. To be able to see this variability in stars, you need a telescope. So here is a picture of a white field, and those stars in this white field. You may not notice anything if you're looking at it with just a white field telescope. You need to zoom in into a patch of the sky to be able to see that. So you can see that this telescope has zoomed in, and you can see the stars that are circled. Observe them that they are changing in brightness. Okay, observe them, they're changing in brightness. Okay, so you can see the variability. And now observe that as it is zoomed in more, it's going to be zoomed in again. So good. So it becomes even more obvious. So you can see the stars changing in brightness. So that is how a lot of stars behave. So we call that variable stars. So, and they are important in astronomy and science. They are important, and I'm going to be explaining that in my next lecture. But I just want to go into uh, some of their classifications first before we talk about their importance. So now, do not confuse variable stars with twinkling stars. I mean, when you look up, if you go outside and you look up to the sky, you see stars that are twinkling. These are not variable stars. That is not how variable stars work. That is not the physics behind variable stars. The reason why the stars are twinkling is because of the turbulence in the atmosphere. So you look at the star from your observatory or from your backyard and you see the stars are twinkling. Everybody has experienced that, twinkling stars. Okay, so the reason why they twinkle is because of the turbulence in the layers of the air or atmosphere. Okay, so that's because of the turbulence. That is why instead of seeing a star like this, we see a star like this. Okay, so do not confuse the two. These are twinkling stars, they're not variable stars. Under this condition, both variable stars and non-variable stars are going to just twinkle. Okay, but what I'm talking about variable stars are what is happening to the star. Okay, if you go closer to the star, you're going to see these things. Okay, so now variability is grouped into two. We have our intrinsic variability and we have extrinsic variability. So what does that mean? So I think we should just focus on intrinsic variability so that we can understand what it means. So in the intrinsic variability, you know, stars change internally. The variability is the from internal, from within the star. Okay, so now it could be caused by many things. Okay, but before we go into that, let us see the classes of these variabilities. We have pulsating stars. We have pulsating stars. So in pulsating stars, maybe I will explain it later. Then we have eruptions. Okay, eruptions can cause intrinsic variability. Okay, eruptions like mass ejections, solar mass ejections. Okay, then we have cataclysmic events, or so like novae and supernovae. So those are intrinsic variability. Those are the things that can cause intrinsic variabilities in stars. So let's say pulsating stars. Pulsating. What does it mean to pulsate? I said pulsating stars are a type of variable stars whose apparent magnitude. Remember, apparent magnitude is how we see it from Earth, how we see it from telescopes from Earth. Okay, how these brightnesses change periodically because the star expands and contracts in a regular cycle. So the star in the background of this picture is an example of a pulsating star. So you see, star expand, contract. Probably we're not used to that because our sun does not behave this way. Okay, our sun does not behave this way, and so we are not familiar with such kind of occurrence. But a lot of stars behave this way, so we call them pulsating stars. So these rhythmic changes occur due to instabilities, okay, instabilities in the star's outer layers, which cause it to pulsate, okay, so that it grows larger and smaller over time. So observe that when it grows larger, becomes red, less energy. Remember the spectrum of electromagnetic spectrum. Bluer is more energy, redder is less energy. So when it contracts, you can see it from a picture there. When it contracts, becomes blue. When it expands, becomes red. Now we have different kinds of stars that behave this way. We have Cepheids, and we have Alare stars. We have long period variables, and we have Delta Scuti stars. So I'm going to be treating, maybe my next lecture, I'm going to be treating these pulsating stars differently. I mean, in more details in my next lecture, but I'm just going to give a brief overview of their characteristics. So for the Cepheid variables, you have they are bright massive stars. Okay, and their pulsation period is between 1 to 100 days. And one thing that is important, one important use of these Cepheid variables is that they are used as standard candles. Standard candles. So when I come in my next lecture, I'm going to explain what I mean by standard candles. So and yeah, it is standard candles are used for measuring cosmic distances. Okay. So some examples are delta Cepheids, even our Polaris, our popular Polaris, the northern star, is a Cepheid variable star. And here's the light curve. Observe the light curve. It goes up, it comes down, it goes up, it comes down. Just very simple. So observe this characteristic so that when we start seeing other light curves, pulsating stars, light curves, you understand, you appreciate their differences. So these are Cepheid variables. So this star that I've been using is also an example of a Cepheid variable. So we have a variable star. So just like Cepheid variables, Cepheid variables are younger, but a lot of stars are older than Cepheid variables. They are older, um, but less massive stars found in globular clusters. Okay, and the period is much less compared to Cepheid variables. The Poseidon period is less than 1 day, and they are also used as uh, distant standard candles to measure distances within our galaxies, within our galaxy and other galaxies. Okay, so they can be used. They are alternative to Cepheid variables. So observe their light curve. Observe their light curve. Look at how it expands rapidly and shrinks slowly. You observe that. Observe that. So that is the pattern of the light curve. It erupts. Sorry, it expands rapidly and slows down gradually. So that's the pattern. So observe these two. This is a Cepheid. It contracts rapidly too, and that is why you have this light curve here. You have this kind of light curve. So then we have. Uh, so look at a globular cluster. See how it is glittering, and the reason why it is glittering is because of these all stars. They are pretty old too, so they make clusters to glitter. And again, these are not twinkling stars, these are variable stars. But if you are observing, you have to be very careful. You have to be very careful. If you do not have a telescope, you can't even see it. Okay, you can't even see clusters with your naked eye. So you need a telescope to zoom in very properly. So we have the mirror variables, or we call them long period variables. So just as the name uh, applies, the variability period is between 100 to 1000 days. That is the variability period. So here the light curve. So see how they are very slow in expanding and contracting. They're very slow in expanding and contracting. Okay, so they are from cool red giant stars. So, and they also have a large apparent magnitude difference. I mean, from the maximum to the minimum, the difference between the magnitude when it is contracted and when it has expanded is large. Okay, so example of this is the Omicron setting. Omicron setting. So we have the data Scudi stars. So they are usually exhibited by intermediate mass stars, and their variability period is within some few hours. And that exhibits small, just very small brightness changes. And here's the light curve. That's the light curve here. So then let's get into eruptive or cataclysmic variable stars. So eruptive eruptive variable stars are stars that suddenly increase in brightness due to violent processes or instabilities occurring on or near their surfaces. Okay, so think about that. So what can you picture what can you picture from such kind of stars? So example, okay, example of such kind of stars that behave, I mean, that, experience violent processes, all of a sudden it flares up. Okay, so examples are novae, right? Novae are supernovae. So, but unlike pulsating stars, unlike those pulsating stars like Cepheids and Alaris, whose brightness changes are regular and rhythmic, okay, eruptive ones, eruptive variable stars, experience sudden irregular outbursts, often linked to either mass ejections, accretion flares, or explosions. So, like I said, examples are supernovae and novae. So, here are some of examples. So, you have a supernova type 2. You can see the picture right there. See how it occurs. So, a star suddenly erupts. Okay, so the light curve of supernovae, rises very sharply, very, very steeply to a maximum brightness, then gradually declines over weeks to months. And it does not repeat. For a supernova type 2, it does not repeat, just a one time event. So that is for supernovae uh, type 2. So you can see the light curve and they're usually coming from massive stars, very massive stars that are, I think, 8 solar masses and above. Then we have a type 1 supernovae. These are supernovae from binary systems. You have two binary systems that one is accreting matter, okay, one accretes matter from the other, and when it surpasses the Chandrasekhar limit, it explodes. Okay, it explodes and destroy the system. Okay, it explodes and it destroys the system. So we call that type 1 supernovae. And here's the light curve of such. The red one, the red light curve. So they are usually from white dwarf, accreting matter. So when the time it passes, it reaches or passes the Chandrasekhar limit, this happens to it. So supernovae. So the two of them they are called eruptive or cataclysmic variable stars. So supernovae are variable stars. Then we have novae. Novae are just almost like type 1 supernovae, but in this process the stars are destroyed. The binary system, the stars of the binary system are destroyed, but in the novae process, the the white dwarf keeps accreting matter. When it reaches the Chandrasekhar limit, it explodes, it becomes less than the Chandrasekhar limit. It continues to accrete matter. I've explained that before when I was talking about stars. If you check my lectures, my past lectures, so you can see how. So in their light curve, there's a steep rise in the brightness over hours to days, followed by a gradual decline over weeks to months. So, but in that relaxation period, so it shows some small bumps or plateau. Okay, so and here's the light curve. Now, if you observe this novel light curve and that of supernovae type 1 light curve, look at supernovae, the red light curve. So they almost look the same. They almost look the same. Okay, so I have created this plot to show you they are different. They look similar, but they're actually different and distinct. So the blue light curve is from type 1 supernovae, while the 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 orange light curve is from novae. So you can see they are different. Now let's go into extrinsic variability. So we have seen intrinsic variabilities are from the internal mechanisms of, of the star. Now, in the extrinsic variability, so something outside the star blocks its light. Something outside the star blocks its light. So we can have eclipsing binary systems. We can have eclipsing systems like planets. Okay, and eclipsing systems, and we have rotating variables. So we'll see them one by one. So in the eclipsing binary systems, you have two stars, like two binary stars. So from our own, from our line of sight, or one goes in front of the other, while the other one goes behind it. Okay. So for the moment, this brightness diminishes, rises. When it rises is when they are separate from our own line of sight. But when it diminishes is when we are one goes behind the other. So for instance, if you observe what is going on here, you will see that when the bigger star blocks the smaller star, we see this big depth in the light curve. But when the smaller star is in front, we see this little bump in the light curve. So the same picture is here. So these are the binary eclipsing binary systems. So here's another example, slower. Okay. So we have eclipsing systems like planetary transit. So here you have a planet passing in front of its host star. So, and that makes it to block some light. So you can see that. So you can see the light curve. So it blocks some of the light. So the flux reduces. So look at the sizes of the planet. If the planet is big enough, let me play the video again. If the planet is big enough, the depth the depth of the light curve will be bigger compared to this one. You can see that. So it tells a lot about the mass of the size of the orbiting planet. Then we have rotating variables. So in this situation, we have a binary systems that are distorted by their mutual gravity. So they form an ellipsoidal shape. So as they orbit, the amount of visible surface area changes, causing smooth double peak light curve. So you can see the light curve of such kind of systems here. Then we have rotating spots. So these stars appear to change brightness as they rotate, often because of spots, bright patches, or non-uniform surface features. So this is the end of my lecture. So in my next lecture, I'm going to be explaining more because there are a lot of details I have not really explained about variable stars. Thank you so much for paying attention.